Bismillahirrahmanirrahim. The selection of the interpolation model or a displacement function is an indispensable step in any FEM analysis. Consider this 1D analysis where the quantity of interest phi is a function of x as shown. Now if we choose as our interpolation model, if we assume a constant distribution, then the best we can do is get a solution like this, because phi is a constant. It can be seen that the error magnitude is quite large, as is to be expected, because the original behavior is anything but constant. Now we can go one step further, and this is what we did in our introduction. We assume that phi is a function of x. It's not a constant, it's a function of x, and it's a linear function of x, alpha 1 plus alpha 2x. You should be very familiar with this kind of expression. Now this will give us something much better. It could give us something like this. Now you can see that this is a linear function. This was constant. Now error in the by the use of maximum error, it has reduced quite a lot. Now we could of course go one step further and assume that the function is a quadratic function, that is alpha 1 plus alpha 2x plus alpha 3x square. And if we do this kind of a thing, then we might get something like this. Now the error in this case, which is the quadratic distribution, this has reduced even further. So as we move along, as we use higher and higher order of approximating function or the interpolation function, the error is reduced. We can go one step further. Phi is a cubic function now, for example. In this way, we can reduce the error between the original situation on the ground and our analysis even further. This one is cubic interpolation function. Now, to reduce error, there is another technique as well. We may use linear elements, but we use a number of linear elements. For example, instead of mimicking this whole domain by one element, we could subdivide it into many elements, so that each element is linear, but their combination mimics the situation very accurately. For example, this could be one element. Now you can see that each of these linear, but by using a number of elements, we can mimic the behavior quite accurately. Now in reality, we use a combination of both these approaches, but the point is that though you are only familiar to this point with the linear interpolation function, this one, but there are occasions where we have to use higher order elements as well. Now when we focused on this linear approximating function, we had to calculate alpha 1 and alpha 2, and for that we needed two equations, and that is why the element took this shape. It's a line element, as they all are. These are 1D and all these are line elements, and there were two nodes I and j. We need to calculate two coefficients, so we need two nodes to get two equations. We have two nodes. Now, if we were to use quadratic function, there are three coefficients to be calculated, and that means that our element will have to take this form. We need three nodes now, I, j, and k, to be able to write three equations and therefore calculate alpha 1, alpha 2, and alpha 3. So you have three nodes. Now, if you were to use the cubic element, you have four coefficients to calculate. So your element, this element has now four nodes. It has to. If I am to calculate all the coefficients. So in this way, there's a correlation between the choice of the displacement function and the shape of the element itself and the number of nodes. Now, this one is linear, and these, anything above linear, these are called higher order elements. As far as phi is concerned, because it's a 1D system, you can say that phi is equal to u, because we are concerned with the one component of displacement only, that is the u component. Now, being a 1D system, these equations have a correlation with this figure. As we increase the order of the displacement function, we get a better and better approximation. But the same thing, without the aid of the diagram, happens in 2D and 3D systems as well. Let's see what happens in 2D. If it's a 2D problem, first of all, line elements are not going to do it. You are familiar with plane stress, plane strain problems. You have to discretize a plane, and you can only discretize a plane by using area elements. So in this case, the linear displacement function will now be a function of not only x but y also, because it's a plane now. As you move along x or y direction, the displacement can potentially change. If it is going to be a linear interpolation function, then it will be a function of x as well as a function of y. Now you need to calculate three coefficients, and the simplest 2D figure is the triangle, and you have three nodes of the triangle, and which fits nicely with our requirement of calculation of three coefficients. So this is the element that corresponds to this displacement function. Now this is a linear function. As we move along towards higher orders, for example, we could write again a function of x and y. We could go one power higher, alpha 1 plus alpha 2x plus alpha 3y plus alpha 4xy. Now we have started the quadratic terms, plus alpha 5x square plus alpha 6y square. Now we have written all the quadratic terms as well as the linear and the constant term. Now this one needs 6 coefficients to be calculated, and that means we need 6 nodes. So if in addition to these 3 nodes which were already there in the linear element, we add 3 more intermediate nodes, we get a number of 6 nodes, again which fits nicely with our requirement. Now this is the, in this case, this is a quadratic displacement function. Now, apart from the dependence on an extra coordinate, y coordinate, there's another difference. Phi in this case corresponds to not just u, but u and v. We have two equations actually. We have just written it in the form of phi, but you could write two equations, one for u and one for v, because now we have two displacement components in this case. Now when it comes to 3D, we are required to discretize volume, so we need solid elements to do the job, but the rest is similar. But a linear displacement function for 3D, first of all, it will depend on x, y, and z axes coordinates, because there are three directions now, and the displacement will keep on changing in all three directions. At least potentially it can. So you need to have, for a linear distribution, alpha 1 plus alpha 2x plus alpha 3y plus alpha 4z. Now you need 4 nodes. If we consider a tetrahedron, that is, it has 4 faces and node on all corners. It has exactly 4 nodes, so it will do the job nicely. And 4 nodes, and this is called tetrahedron. Now this is the linear displacement function. Now if we go towards the quadratic, we need to include the second powers. Again, a function of x, y, z. It's a long one, alpha 1 plus alpha 2x plus alpha 3y plus alpha 4z plus alpha 5xy. This is the first quadratic term, plus alpha 6yz plus alpha 7zx plus alpha 8x square plus alpha 9y square plus alpha 10 z square. Now we have exhausted all the quadratic terms as well, and of course the linear terms are also there along with the constant term. So this is the quadratic variety of solid element. Now we need 10 nodes, and again you can see that if this tetrahedron that we have already considered, apart from the 4 nodes at all the corners that linear element has, if we add nodes everywhere in between also, and we can count 1 2 3 4 5 6 7 8 9 10, exactly it will do the job. So this is the higher order variety of tetrahedron element. As we go towards higher order elements, whether it's 1D or 2D or 3D, we need more and more nodes. That is because we need to calculate that many more coefficients. Again, to avoid writing everything thrice, we have used the symbol phi, but phi for 3D problems stands for U, V, and W, because all the components of displacement follow the same variation. Now, there's a correlation between the shape of the element, the number of nodes it has, and the displacement function we are using. So let's classify elements according to these considerations. Of course, elements can be classified in many different ways. One classification is very obvious, 1D, 2D, 3D. Another classification could be element for stress analysis or element for heat transfer problems. So there can be many classifications, but we are going to consider one specific classification here. Now the classification we are talking about is, we have 3 types of elements: simplex, complex, and multiplex elements. category, and this is element. Let's start with the simplex element. A simplex element is a linear element, that is, it has linear and constant terms only, and nodes at corners, ends or corners. You're already familiar with them. The element you did in your introduction, ij, two nodes, 1D element, it was a linear element. You have just, for 2D systems, you have just seen this triangle with the nodes at the three corners, I, J, K. This is a simplex element because only linear and constant terms are there and nodes are only at the corners or the ends. You have also just seen a tetrahedron. We're talking about 3D here. Linear and constant terms and nodes only at the corners. These are simplex elements. Now, simplex may be a fancy word, but all it means is an element which doesn't have higher order terms. 1D, this is 2D, this is 3D, all are simplex elements. Now we come to second category, that is complex elements. Complex elements have the same shape as the simplex elements, but with higher order terms. But with higher order terms. So this means the difference between simplex and complex is that the shapes are the same, but complex elements will use higher order terms. We have just seen some higher order displacement functions, and if you talk about 1D, then this is a higher order element because you have three nodes, and this means that quadratic function has been used. If you go one step further, and we have just seen it, this one too. Again, this is a higher order element because you have two nodes in between. But the shape is the same, it's a line. When it comes to 2D, and we just saw this one also. The shape the same as the simplex element, but we have more nodes because we need to accommodate more terms because it includes the quadratic term. This is a higher order element. And when it comes to 3D, again we just saw this higher order tetrahedron. Same shape as the simplex element, but to accommodate more terms, there are more nodes, and the nodes must equal the number of coefficients to be calculated, and those coefficients depend on the number of those coefficients depends on the order of the polynomial. So we have just seen this one as well. Now these are two categories. What about the third one? What is multiplex? Multiplex elements have higher order terms. So these are also higher order elements, but they have truncated polynomials. Let me explain this in a minute. Let's consider a 2D element, a very popular element at that, square or a rectangular element with 4 nodes. Its displacement function is this. Now, it is not linear. There is a quadratic term, but the polynomial has been truncated. We have not included the x square and the y square term. Why? Because if we include that, we get 6 coefficients, but there are only 4 nodes at the corner. And if we add nodes in between, then we get 8. So there's a mismatch in either direction. So what we do is truncate the polynomial and make the number of coefficients equal to the number of available nodes. Another variety, same shape, rectangular element, but this time we have the nodes in between as well. So you have 8. Now if you go on to add the second order, the complete second order terms, you'll only have 6 terms. But if you go on towards adding the cubic terms, then you will end up with 10 terms. But the nodes available here are 8 only. So because of the mismatch, again for this kind of an element, you'll have to truncate the polynomial at the appropriate place. Now when it comes to 3D, a manifestation of the multiplex element will be something like this. It's called a hexahedron. It has 6 faces. This is also called brick element for obvious reasons. Now this has corner nodes. Now you can verify for yourself that you need to truncate some of the terms of the polynomial in order to accommodate these 8 nodes. Now multiplex elements have a flexibility that complex elements don't have. You need to use all the terms in a complex element, and therefore there are restrictions there. But in multiplex elements, you can just cut off the unwanted part of the polynomial, and this gives you great flexibility. That is why multiplex elements are used extensively in FEM. Now, although we will deal with the complex and the multiplex elements, that is the higher order elements, near the end of the course, for now our focus will be squarely on simplex elements. The reason being, they are easy to handle, especially their integration. They can be integrated exactly. There are simple formulas to integrate simplex elements, and that makes life easier for us. Now, as compared to this, the higher order elements, this would include multiplex as well as complex elements. The higher order elements need to be integrated numerically. Now, this could give you exact solution, but more often it gives you an approximate solution. Once we are done with simplex elements, we'll take up higher order elements, and before that we'll just brush up on our numerical integration skills, which is not a very difficult thing to do. Thank you.